It's 3 in the morning, production is down, customers are angry, and your dashboards just say everything is green. This is the nightmare that observability is built to prevent. So today, let's design a complete production-grade observability platform from the ground up. We'll move slowly and clearly, one piece at a time, and follow the same structured approach engineers use in real system design interviews. Let's begin. First, what even is observability, and how is it different from plain old monitoring? Monitoring is a black box. You decide your questions in advance and build a dashboard for each one. It can tell you that a service is up or down, but when something new breaks, it leaves you blind. Observability turns that black box into a glass box. By collecting rich data from inside your systems, it lets you ask brand new questions about your live system and debug problems you never anticipated without shipping a single line of new code. Monitoring tells you that something is wrong. Observability tells you why. Now, designing a system this big can feel overwhelming, so we'll follow a clear blueprint. It's a well-known interview framework called RESHADED. We start with requirements, then estimation, the rough math of our scale, then storage and the data model, then the high-level design, then the APIs, then a detailed deep dive into the tricky parts, and finally evaluation where we weigh the trade-offs. 7 clear steps. Let's take them one at a time. Step 1, requirements. Before we design anything, we have to agree on what this platform actually needs to do. Let's start with the functional requirements, the concrete features. First, the system must ingest telemetry, that is, collect metrics, logs, and traces from thousands of services. Second, it must store that data efficiently, keeping recent data fast to access and older data cheap to keep. Third, it must let engineers query and visualize everything through dashboards and ad hoc searches. And fourth, it must alert a human the moment something genuinely goes wrong. Collect, store, query, and alert. Those 4 verbs are the heart of the platform. Now the non-functional requirements, the qualities that make it trustworthy. It must be highly available because an observability tool that goes down during an outage is worse than useless. It must be low latency so that data appears within seconds, not minutes, when every second of an incident counts. It must scale horizontally to absorb a relentless, growing firehose of data. And critically, it must be reliable under pressure. When your whole infrastructure is on fire and flooding it with data, that is exactly when the platform must not fall over. Step 2, estimation. Let's get a feel for the sheer scale of data we're dealing with, because that scale will shape every later decision. Let's do some quick back-of-the-envelope math. Imagine a fairly large company running 10,000 servers. Say each one emits around 10,000 metric data points every 15 seconds. Multiply that out and you are ingesting on the order of several million samples per second. For reference, Airbnb's real pipeline handles over 100 million samples per second. Now logs. A mid-sized platform can easily produce 10 billion log lines a day, which is roughly 100 terabytes daily. The largest systems, like OpenAI's, ingest petabytes of logs every single day. The takeaway is simple but profound. This is a write-heavy, high-throughput firehose, and that single fact drives our entire architecture. Step 3, the data model. To design the storage, we first have to understand the 3 fundamentally different shapes of telemetry data. These are the famous 3 pillars of observability. The first pillar is metrics. These are numbers measured over time, like CPU usage or request latency. They're tiny, cheap, and easy to aggregate, and they're how you detect that a problem exists. The second pillar is logs. These are detailed, timestamped records of discrete events. They're how you diagnose what actually happened line by line. The third pillar is traces. A trace follows a single request as it hops across all your services, so it shows you where the time went and which service is the bottleneck. Metrics detect, logs diagnose, traces locate. You need all 3. But here is the key insight that ties them together. A single user request, as it flows through your gateway, your auth service, your orders service, and your database, emits all 3 signals at once. The magic is that every one of those signals can be stamped with the same shared identifier, called a trace id, so when latency spikes, the metric, the error log, and the trace span all carry the same id. That shared id is the thread that connects the 3 pillars into a single story. And how do we capture all 3 signals in a consistent way? The answer is OpenTelemetry, the open industry standard from the Cloud Native Computing Foundation. With one set of libraries and one data format, your application emits metrics, logs, and traces together, each carrying that shared trace id. This is what makes real debugging possible. An alert fires on a metric. You click straight to an example log line. That logs trace id opens the full trace. And the trace points to the exact SLO database call, from symptom to root cause in seconds, not hours. Step 4, the high-level design. Now we can finally draw the architecture, following the data from creation to alert. Here's the end-to-end pipeline in 5 clear stages. Stage 1, collection. A lightweight agent, usually an OpenTelemetry collector, runs alongside your apps to receive, batch, and forward their telemetry. Stage 2, the pipeline. Everything flows into a buffer like Kafka. This is crucial. When a traffic spike floods the system, Kafka absorbs the surge so data is never dropped. Stage 3, storage. Here the data splits because each signal needs a different kind of database. Metrics go to a time series database. Logs and traces go to their own specialized stores. Stage 4, the query engine, a single layer that lets you read across all of them. And Stage 5, the consumers, dashboards for humans and an alerting engine watching for trouble. Collect, buffer, store, query, alert. Step 5, the APIs. Let's define the 2 contracts the platform exposes to the outside world. There are really just 2 interfaces. The right path is a push. Agents stream data and using the OpenTelemetry protocol, sending metrics, logs, and traces in batches that are compressed and sent asynchronously, so your application never has to wait. The read path is a pull. Engineers ask questions using query languages, PromQL for metrics, LogQL for logs, and similar languages for traces. Those queries power every dashboard, every alert, and every late-night debugging session. A simple, high-volume write path in, a flexible, expressive read path out. Step 6, the detailed design. Let's deep dive into the 3 hardest problems that make or break a platform at this scale. Deep dive number 1, storage tiers. We simply cannot afford to keep every high-resolution data point forever, so we use tiered storage with downsampling. The hot tier keeps raw, per second data in fast memory or SSD, but only for the last few days. As data ages, we downsample it. The warm tier keeps per minute averages for a few months. The cold tier rolls that up to per hour and parks it in cheap object storage like S3 for a year or more. And a frozen tier archives it for compliance. Recent data stays fast and detailed. Old data becomes cheap and coarse. That balance is what makes the economics work. Deep dive number 2, and this is the single most common way teams destroy their metrics system, cardinality. In a time series database, every unique combination of labels creates a brand new series, and memory grows linearly with the number of series. Look at this. A metric with 50 roots and 5 status codes is harmless. But the moment someone adds a label like user id with 10 million possible values, you multiply out to billions of time series and the database falls over. The rule is ironclad. Only put bounded, low cardinality values in labels. Things like user id, email, or trace id belong in your logs and traces, never in a metric label. Deep dive number 3, alerting that doesn't drown your team in noise. The secret is to alert on user experience, not raw machine stats. We start with an SLI, a service level indicator, which measures what users actually feel, like the percentage of requests served under 300 milliseconds. We set an SLO, the target, say 99.9%. That leaves a tiny error budget, the small amount of failure we can tolerate, which at 3 nines is about 43 minutes a month. And then, crucially, we only page a human when that budget is burning fast. A slow burn becomes a ticket for tomorrow. This single idea is what kills alert fatigue and keeps your on-call engineers sane. Step 7, evaluation. Every design is a set of trade-offs, so let's name them honestly and then map the whole thing to real tools. There are 3 trade-offs you can't escape. First, sampling versus completeness. You can keep every single trace and pay a fortune, or sample a fraction and risk missing the one you needed. Most teams use smart, tail-based sampling to keep the interesting ones. Second, cost versus retention. Longer history is invaluable for debugging trends, but storage isn't free, which is exactly why we tier and downsample. And third, detail versus cardinality. Every rich label you add makes data more useful, right up until it explodes your database. Observability is the art of balancing these 3. Finally, let's connect every layer to the real tools you'd actually use. For instrumentation and collection, OpenTelemetry. For the pipeline buffer, Kafka. For metrics, Prometheus, and at scale, Mimir, Victoriametrics, or Thanos. For logs, Loki, Elasticsearch, or ClickHouse. For traces, Temp or Jaeger. For cheap long-term storage, S3-style object storage. For dashboards, Grafana. And for alerting and on-call, Alert Manager wired into PagerDuty. Notice the pattern. OpenTelemetry in the front, Grafana at the back, and a purpose-built store for each signal in between. So let's bring it all together. We followed RESHADED from requirements to trade-offs. We built around the three pillars: metrics, logs, and traces, unified by OpenTelemetry and a shared trace ID. We designed a 5-stage pipeline: collect, buffer, store, query, and alert. We tiered our storage to control cost. We tamed cardinality to protect the database, and we alerted on error budgets to protect our people. That is a complete, production-grade observability platform. Because in the end, you simply cannot fix what you cannot see. Thanks for watching.